Hey learners, Jared here, and today we're going to continue our investigation into direct current circuits, and specifically we're going to look at Ohm's law. Now, Ohm's law, I use law loosely because again, with most things that we do in physics, we build a model and that model works for most of the time. Ohm's law isn't a law end-all be-all where it will work in every scenario. There are other factors at play, but this is a great place to start your analysis into a circuit. Ohm's law is written as your voltage is equal to the product between your current and your resistance. Now, this will work for an entire circuit with an equivalent resistance, and it will work down to individual resistors in that circuit. Knowing how these three things are related will help you analyze a circuit faster and be able to give you kind of that big picture understanding of a circuit. Let's take a look at this simple circuit where we've got a battery hooked up to a single resistor. With these values for the battery's voltage and for the resistor, we have a particular current in that wire, and it's following Ohm's law. Swapping out the resistor for, let's say, a higher resistance, well, how is that going to affect the other factors in that circuit? The voltage of the circuit is determined by the battery. And if I don't change the battery, then I'm not changing the voltage of the overall circuit. So that voltage, that V, is locked in place. It can't change. Increasing the resistance, though, is going to change the current of the resistor. They're actually inversely related to each other. Because of the fact that voltage can't change because the battery is the same, increasing R resistance is going to decrease I, the current in that overall circuit. Now, what if I change the battery? If I swap the battery out for, say, a lower voltage? Well, doing that, if I keep the resistor the same, lowering the voltage, I've decreased one side of the equation, which means I've got to decrease the other side. The resistance of the resistor is an independent factor. It's not going to change based on the battery. Again, neglecting temperature and things like that, which we'll talk about soon. Decreasing the voltage is going to decrease the current. The two things are directly related. And they're actually, if I cut the voltage in half, I'll cut the current in half because the two are directly proportional to each other. And we can use this linear behavior, this ohmic behavior, to figure out the resistance of a particular resistor. For instance, an experiment that we will do, we will take a resistor of unknown value and we'll hook it up to our circuit. And we'll increase gradually the voltage applied to that resistor. Well, things that we can measure easily are voltage and current. So if we know the voltage and we know the current, we ought to be able to figure out the resistance. And it's a linear behavior. If we plotted that data, voltage on our vertical axis and current on our horizontal axis, the only thing that's left is resistance. And since that is a constant for the behavior that we're going to be analyzing, the ohmic range of that resistor, the slope of that line will tell us the resistance. The bigger the resistance, the bigger the slope of that line. The more voltage it's going to take to get more current out. Now again, Ohm's law depends on whether a resistor behaves ohmically. That is, it actually abides by Ohm's law. And again, law, I would like to swap that out for model. It fits for a particular range of values. What we'll look at next is what determines that resistance for that particular resistor. In other words, why does it have that particular resistance? We'll get into that next time, and as always, keep learning.